Alright, welcome to my next video on classical mechanics, and this one's going to be about deriving kinematic equations, and I'm going to do this with constant acceleration, but I'm going to challenge you at the end to do it without constant acceleration, and I think you'll see that the same process will still work. So first, before I do this, I want to introduce the concept of the integral. Now the integral will occasionally be called the anti-derivative. This means that we're doing the exact opposite process as taking the derivative. Okay? So, deriving kinematic equations. Here we go. So, what I'm going to do is I'm going to write my acceleration as a function of time. That just means that acceleration depends on time. But here we're going to see that it really doesn't. Because the acceleration is a function of time, well, acceleration is just going to be a constant. So we're just going to write a. Okay? So what we want to do is we want to take this backwards. So if you remember my little chart from last time with x, v, and a, I would show that the derivative with respect to time could take you from x to v and from v to a. Position to velocity, velocity to acceleration. Okay? Well, what if I want to go backwards? Well, the integral is the antiderivative. That's going to do the exact opposite. So we're going to take the integral with respect to time. And that dt is how we write it with respect to time in this format. So we're going to take the integral with respect to time of acceleration to get velocity, and the integral with respect to time of velocity to get position. Okay? Okay, so now I'm going to multiply either side of this equation by dt. And what we find is that the acceleration as a function of time, dt, equals the acceleration magnitude dt. Okay? And I'm going to integrate both sides with respect to time. And well, we already said that the integral of acceleration with respect to time is going to be velocity. So we can just write this as velocity as it depends on time. And this time velocity really will depend on time. So what I'm going to use here is something called the power rule. Okay? And this is the most simple rule for derivatives and integrals. For a derivative, we'll say that we have some constant k, which will just be a number, times x, and x is going to be raised to the nth power. Well, if we want to find the derivative of this, the derivative with respect to x in this case, what we can see is that it's going to be n minus 1 times k, and then times x to that n minus 1 power. We're going to have to do the exact opposite for an integral, because it's the antiderivative. Here, the integral of k times x to the n with respect to time is going to be equal to k times x to the n plus 1, adding 1 this time, all over n plus 1. All right? And we are also going to add a constant c, because we could, remember, the derivative of any constant is 0. So if we're going backwards, we could have a constant in this equation that would get taken out. So if we had a constant right here, if I added plus c, it would just get eliminated by the derivative, because the derivative of any constant is 0. The rate of change of any constant is 0. So we want to make sure to add a constant back in when we do something called the indefinite integral, which is what this is. A definite integral would have specific bounds at which our function that we plug in is evaluated at. So a definite integral would look like this. Maybe from 0 to 1, right? Whoops, can't see that. From 0 to 1. And here we do not need c. Okay? But we're just doing indefinite integrals, so we're going to use c. You can do this using definite integrals, but I think this is just much faster and much easier. So, now, if we take the integral of this, well, we don't have a t in there, but we're going to basically say that we do have a t, and that t is at the power of 0. When something's at the power of 0, it's always equal to 1. So t to the power of 0 is equal to 1. So we're just multiplying a times 1, which is just a. So we can do this. Now if we add 1, what we will find is that we just get a times t to the first power, which is just t. Remember to add your constant, which in this case is going to be our initial velocity. So if time equals 0, that term equals 0. Cover that up, we just get our initial velocity. Okay? V naught is what I would call this. So we add 1, and then we divide by 1, which is just that value. So it's just at. Now we're going to integrate again. Okay? And I'm going to add a dt to either side, because it's incorrect to not have that at either side. One day I'll learn to not hit the camera with the pencil while I erase. One day. But that day is not today, apparently. So, now, we're going to get the position as a function of time. Because remember, if we take the integral of velocity, we get position. Okay? And now here we have the power of 1 on this t. And once again, we can really say, I'm actually going to erase that, and oh, I learned. And now I'm just going to move this down here. So we have the integral of a times t to the first power plus the initial velocity times t time to the 0th power, which again is just 1. So it's really just the initial velocity. Always add your dt. Okay. Now, what we can do with this is, well, we can add 1 here. Okay. And we get at squared divided by that 2, because 1 plus 1 is 2. We're just going to divide by that 2, which I'm going to write as multiplying by a half. Okay. So 1/2 at squared. We're just going to do the same thing over here that we did up here. So this will just be plus v naught, or initial, however you want to say that, times time. And now we're going to add some initial position in case time equals 0, our starting position. And we find that position as a function of time equals 1/2 times the acceleration times the time squared plus the initial velocity times the time plus our initial position. Okay? And that is a kinematic equation for constant acceleration. Now, what I want you to do is to try to derive an equation for position as a function of time where acceleration does actually depend on time. We're going to say it's some constant b times t. I'm going to specify this as a constant. Okay? All right. Just as one final little note, all of this will work in 3 dimensions. So we can also write here that the r of t, our 3D position vector r, is just going to be equal to 1/2 acceleration times time squared plus v naught times t plus r naught, our initial position. And we could write this for y, we could write this for z. It's going to be the same thing. So that's going to do it for this video. I really do encourage you to try these challenges that I leave at the end of the video, because they will help you think like a physicist. They will help you think like you're solving a problem set, which, to be honest, most of you probably have to solve problem sets, as I imagine if you're watching this for school. Though, hey, if you're watching this on your own time for your own enjoyment, props to you. So that is going to do it for this video. I really do hope that you have a good day, night, afternoon, whatever time you're watching this, wherever you are. Enjoy your life. Get out there, do something fun. All right, see ya.